In this video, I'm going to look at a short R script to just sort of get used to working with vectors, and it also happens to test the small angle approximation. So here's the idea of the small angle approximation. Here's the Wikipedia page. That the function sine of theta or tangent of theta can be replaced with just theta, provided that you're working with angles in radians for small angles. And so we're going to play with vectors in R to see like how small is small in terms of this approximation. So here we go. So I've decided to go up to 30 degrees to see. So it said radians, but I'm going to start in degrees, convert to radians, and then look at this uh, approximation. So I decided I'd go up to 30 degrees. So I've used this SEQ, this sort of sequence method to produce for me a vector with the numbers 1 through 30. Now, this sine is equal to sine of 0 is 0 and tangent of 0 is 0. So 0, it's just true, like flat out true. So I'm not going to put in 0 here because at some point I'm going to be calculating the percent error and I'm going to be dividing and I don't want to divide by a 0. So I'm starting at 1, not 0. Okay. So this is just going to generate, this is mostly comments and just a few lines of code, but this tells you like how good is at working with vectors. Okay. So just run this line 7 here. I'm going to get this vector with the numbers 1 through 30 in it. There it is. Okay. So we can see that over here. Uh, just goes the dot, 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 but there are, does go up to 30. Now, the small angle approximation, as they said, involves working with the angle not in degrees, but in radians. And so, like halfway around the circle is 180 degrees and pi radians. So, if you want to convert to radians, you multiply by pi, you divide by 180. And so, we're doing that here. And the nice thing uh, in R when working with vectors if you sort of apply some operation, um, say multiplication and division in this case, it just does it for every element of the vector. So it's going to do it to 1, then it's going to do it to 2, then it's going to do it to 3, all the way up to 30. So now here are those all those 1, 2, 3 given to us out in radians instead of degrees. But again, in sort of older programming languages, you'd have to sort of explicitly write a loop and go through every element and add append an element to the new vector that you're making. Um, and all that's happening here, but you're sort of not responsible for explicitly writing it. You can just sort of write this tiny little equation in terms of vectors, and it just understands, apply this operation to each element. And even if it's a more complicated function than or action or operation, so here our operation was multiplying by pi, sort of multiplication and division, sort of fairly elementary operations, but even uh, an operation like taking sine, it's again just the same principle. It's just going to take the sine of all of those angles. And when you work with in computer languages, when you work with sines and cosines, etc., you want the angles to be in radians. That's typically how it works. So this, I'm going to get a vector called sine underscore ANG for the sine of the angle. And I'm going to get it by taking the sine of the angles that I figured out just above in radians. So run that. And so now I have my angles in degrees, my angles in radians, my the sine of my angles. Okay. Now I'd like to figure out the percent error. So I'm imagining that I have something where sine of an angle came up, and I'll say X, sine of X came up, but my life will be easier if I can just replace the sine of X with X, and I want to know sort of how good that is. So I'm going to calculate percent error. What error would I be making by making that substitution? So I'm going to take the sine of the angle minus the angle in radians. So that's the difference. I'm going to divide it by what I really wanted it to be, which was the sine of the angle. So this is a percent error. I'm going to take the absolute value. So I'm not going to worry. I'm just going to imagine all the errors take the absolute value, we'll get a positive. And then I'm going to just multiply it by 100 to sort of see it as a percentage. So run that. And so then here are these percent errors. Now this is nice. It's done all these repeated calculations for me very conveniently. Again, this looks complicated, but it's mostly me being long-winded with comments. I've really only run 4 lines of code. Um, but I want to just make it look nice. This isn't very good for comparison over here. So I'm going to use a method in that R provides called cbind. And it's just going to sort of put these vectors, I'll call them parallel vectors, sort of into one larger unit, a matrix, if you will. And then I'm going to print out that matrix down here in the console. So run that. So now I have this combo thing. So these were simpler structures, vectors, but this is a somewhat more complicated thing. So they've sort of made a little bit of division over here. Finally, we're just going to print it out, which will put it down in the console. And now we can sort of see sort of element by element. Here was a degree of 1, there's the radians, and there's the sine of the angle, and there's the percent error. And then we can sort of, like, there's no fast answer for how high an angle is this the small angle approximation good. It depends on how much error you're willing to tolerate. So we can sort of go down through this list and say, let's say I'm willing like 1%. I don't mind if I make a 1% error in my approximation. So if I'm going to replace sine of theta with theta, I expect to make that to be a 1% error. I can go up to sort of just shy of 14 degrees, this suggests. And say if I was going to go up to 5 degrees, sorry, 5%, if I was allowing an error of up to 5%, then I can go even a bit higher than a 30-degree angle. So again, so this approximation is sort of well known, but you can use this little script to figure out, sort of pick and that's sort of a tolerance, if you will, a percent error that I'm willing to put up with, and then figure out how big the angle can be and be within that tolerance. Um, and it's really just a demo of vectors in R. So I can use SEQ to, if I have just a simple sequence of numbers and I want to create a vector from, they make that easy so I don't have to type 1, comma 2, comma 3. It'll do it sort of for me. Any simple operation that I apply to a vector gets applied to all the elements. So here it was multiplication and division. Here it was taking the sign. Here it was taking one vector minus another divided by a third. I mean, not a third, but one of the vectors again. So I'm taking the difference. I'm taking the absolute value. I'm dividing by a vector, multiplying by 100. But it's just simply do that to every element. Um, I can combine my parallel vectors into something more complicated. And I don't really want to do anything with this more complicated thing other than display it. So I make this more complicated object just because it's convenient for display. And then I do go ahead and display it, print the combo, and that put it down here in the console, giving us this sort of nice listing of the various angles. It allowed us to sort of pick out uh, degrees that we could go to for a particular tolerance. Okay, that's what I wanted to show you with this one. Thanks for your attention.